ride home on Friday.
I remember that.
Yeah. I'm just like
Okay.
I'm just trying to
Fair
get
enough.
stuff done. I'm busy. Constant.
Facts.
Alright, kids, so here we go.
So he doesn't want it.
So, does anybody have any specific questions on the lab? Yes, just,
Number 9.
no. The car with mass. Okay. So here's what you've got going on number 9. So here's this car, right? So start with, if you don't know what forces are acting on the system, you can't do anything. So if you come up and you say, hey, I don't know how to do a particular number. Here's the first thing I'm going to ask you. Have you drawn all the forces acting on the system? Because if you haven't, then you're dead in the water, okay? So here's this car, right? Obviously we have gravity pulling it down, right? We have the force normal acting upward, right? And the car is going in this direction, okay? Already going in this direction. And we're going to stop the car. So what's the direction of the frictional force going to act? Yeah, to the left, right? So I'm going to have some frictional force acting back this way. Now, what you're tempted to do is that you're tempted to say, well, the car is moving in this direction, so there's also like an applied force going in this direction. Don't confuse inertia with a force, okay? Inertia is not a force. Yes, this car has a large mass, 950 kilograms. This car really wants to keep going in a straight line at a constant speed, okay? That's what wants to happen because it has that much inertia. But there's no force going in that direction unless you're pressing down on the gas pedal. But you're not. You've hit the brakes. So the only force acting on the system is going to be this frictional force going in this direction. So, in this situation, the first thing you need to do is find the acceleration. Because that's the whole point. When you look at a velocity time graph, okay, so like in this situation, this velocity time graph is starting at 15 meters per second. So, one of 3 things could happen on this velocity time graph. It could go up, meaning that the car is going to go faster. It could be a horizontal line indicating that we're not accelerating and all the forces add up equal to 0. Or it's going to slope down and approach 0. So anytime you have a velocity time graph that's not a horizontal line, that means it's accelerating. That means that the forces don't add up equal to 0. So Jennifer, what's the velocity time graph going to do?
It's going to go down.
Okay, so I know I'm going to have then a negative acceleration, right? So you know how fast it's going, you know a distance, right? So you need to find the acceleration. So use that equation. So you've got v squared equals u naught squared plus 2ad. And that acceleration should be around like negative 5.5, okay? So, because if that acceleration is wrong, everything else is going to be wrong. So then on B, you want to find the value of this frictional force. Well, any force, as long as it's causing an acceleration, can be written as mass times acceleration. So you're going to take mass, 950 kilograms, multiply it by the acceleration that you found, okay? So this is one way that you can calculate force friction. In this situation, we're going to calculate forced friction by taking mass times acceleration, okay? Then, once you get that, then last thing you want to do is calculate mu. Well, mu is going to be forced friction over force normal. On a flat surface, force normal is the same as your gravitational force, which is going to be mg. So, to get this, get your frictional force, multiply the mass, 950 kilograms, multiply that 950 kilograms by that acceleration. Then, to get the normal force on a flat surface, which this is, that's the same as your gravitational force, which is just going to be mass times your gravitational acceleration. Now remember about mu. It's an absolute value. So even though this frictional force is technically going to be a negative value, it doesn't make any sense to make mu a negative value because mu is just a ratio, it's just a number. Okay? So find your acceleration using that equation. V squared equals z naught squared minus 2ad. Multiply that by the mass, there's your frictional force, divide the frictional force by your force normal. There you go. So if all goes well, that mu should be around 0.6. Okay, that's an ish, but it should be somewhere around 0.6. Anything else you want me to go over?
Did mu, does it have a unit?
No,
Is it
because it's just
doesn't?
because it's newtons divided by newtons.
Alright.
So mu has no units. It's rarely equal, even equal to 1, let alone exceeding it, and it's always a positive value.
Okay.
Okay? Now, here's what I want in terms of diagrams. Calvin, listen to me. So, with the box moving at a constant velocity, you're going to draw a free body diagram, but you're going to have Fg, force normal, force applied, force friction. This is drawn with a ruler where you're going to let 2 centimeters equal a newton. Okay? So like if your gravitational pull, these blocks are usually weighing around 3.8 newtons. So you would draw that like 7.6 centimeters long. This is not a sketch. This is drawn with a ruler to an exact measurement. I want to see what the forces are. Okay? So this is what this free body diagram is going to look like. I want it done with a ruler. This is not a sketch. But if I say sketch it, I mean sketch it. I don't care. This one you're doing with a ruler. Then you're going to draw them tip to tail. And that's going to look something like this. Okay? And you should end up back at the origin. So if you end up back at the origin, that means the system is just in equilibrium. It does not mean that you're at rest. Okay? It just means that you're not accelerating. So if you draw these, anytime you draw these tip to tail, you can only end up with one of 2 options. You either end up back at the origin and you're at a constant velocity, or you don't end up at the origin and you begin to accelerate. That's it. Those are only 2 things that can happen. Then on that free body diagram for the force table, okay, you should have one diagram that looks like this, A, B, C. And then the other one is you're going to draw that, A, B, C, tip to tail method. And hopefully you end up somewhere close to that origin. So that's what the second set of diagrams is going to look like. And then you're going to have a graph that's going to look something like this, where you can have force friction here, force normal here. You're going to have some data points. You're going to draw a line of best fit. And here's what everybody's line is going to be different. Circle the points that you're going to use to find the slope, write them down, and then show me that calculation of slope. Okay? And now, you can only use your data points if they happen to be on the line of best fit. If your data points aren't on the line of best fit, you can't use them. That's the whole point of drawing the line of best fit. Okay? Everybody cool with what I want? We're good. Going once? No questions? Yes?
11.
What's 11?
It says, what are 3 ways to determine the force friction?
Well, let's go through those. So one option is that you did in the lab, you pulled the block, and you measure how much force it took to pull it, right? And then your force friction is opposite of that. So that's one option. We just did this, where we had, you look at this, mu equaling force friction over force normal. So if you know what the force normal is and you know what mu is, you can multiply mu by force normal and get it that way. And then the last one is what you did on that one that Jennifer asked for at the beginning. You can multiply mass by the acceleration that it causes. So either pull it, or use mu, or use mass times acceleration.
Okay.
Okay? Anything else? Going once, going twice? So get those just by, even if it's by like 9 o'clock tonight, that's fine. You should about have it done. You've been working on it for like 2 days now. And a week. Okay. So to kind of show how forces balance out, and this is pretty sensitive in terms of if it works or not. So what this is a really strong base magnet here, okay? And this is also a magnet. So if I throw it anywhere close to it, it sticks, okay? So what I'm going to do is, if I just put it up here and let go of it, it doesn't stay. But if I get it spinning, fast enough, and if everything is just right, I'll hover. Okay? You have to, yeah, everything has to be just like within basically. Whoop. That's the hardest part, is getting this thing to spin, by the way. So what's happening is that you have two opposing forces. You have the gravitational force that's pulling it down, and then you have the repulsion created by the magnetic field. And the reason it slows down is that you have an interaction of the magnetic field of this with the magnetic field of the base, and that dissipates energy. You can't see it, but that magnetic field is there. So when that thing is spinning fast enough, what happens is that you have a balance of these forces. You have the gravitational force pulling it down, and then you have the magnetic repulsion, which is making it try and fly away. So in that one sweet spot, when you're spinning just fast enough, and those forces are balanced out, you have a system where it's in equilibrium. So that's a situation where there are forces acting on it, but it's just not accelerating, okay? Because all the forces are balanced out. So I'll try one more time. There you go, that's a good one. That was actually, oh great, you ruined it. Great, I had it going. Fantastic. Okay, so what we're going to do today is we have some various demos dealing with Newton's 3 laws of motion. All right? So in the back, in case you haven't noticed, there's a bed of nails back there. And here's what's going to happen. I'm going to lay on the bed of nails, okay, like this. Then I'm going to take a concrete block and lay it on my chest, and then I'm going to put my life in Ricky's hands, and I'm going to have Ricky smash the block with a big hammer, okay? Now, before I do this, I want to make sure that we're cool with Newton's laws of motion, right? So, if you look at the concrete block as a system, with me part of it, okay? So, that concrete block has a large amount of mass, okay? And so do I. Probably more than I should. Few too many quarter pounders, but hey, life is short. So, that wasn't that funny, Ricky. But,
I just wasn't ready for it.
oh, okay, all right, next time we'll take Ricky, I'm going to say something funny. Get ready to laugh. Okay. So, my body has a certain amount of mass, right? So does the block. So when he hits it, my body is going to resist a change in that velocity because it has mass. I don't want to accelerate very much, okay? I want to minimize my acceleration. Okay? It can't be zero, but I want to minimize it. So now we're going to jump to the third law. Third law says that for every force, there is an equal and opposite force. So for every action, there is a reaction. So in this system, let's define down as being negative and up as being positive. So when Ricky hits me with the hammer, okay, he's going to exert a negative force on the block, right? So by Newton's third law of motion, what does the block have to do?
Exert a force on the hammer.
Exert an equal and opposite force upward on the hammer, right? So I'm going to have a negative force acting downwards, so there has to be a positive force acting upward, okay? Now, don't sit there and go, well, can't, you and the block, that's a lot of mass, Hammers, not so much. Doesn't make any difference. There's no conditional statements to Newton's third law. It isn't, only if the masses are the same, or only if there's just a little bit of difference between the masses. No, it's for every action, there is a reaction. Forces are coupled, okay? Now, when the sledgehammer hits the block, okay, now think very carefully before you answer this. When that sledgehammer hits, do I want the sledgehammer to accelerate?
Yes.
Yes, because if it doesn't, what's going to happen?
You're gonna get a sledgehammer cut through you.
Yes, because I want that sledgehammer to accelerate, but I want that acceleration to make it do what? Slow down. Okay, because if it doesn't slow down, and it doesn't accelerate, somebody's calling Notre Dame and going, this is why probably Mr. Burkamp has a sledgehammer stuck in his chest. I'll be right down. I'll test him for COVID. Okay? And here's some ice chips. We'll take it. No, I've got a sledgehammer in my chest. Okay. So I want that sledgehammer to accelerate. I'm going to accelerate as well, but I don't want to have a big acceleration, because if I do have a big acceleration, I'm going to end up impaled on the nails. Okay, that's going to be bad. Okay? So what I'm banking on is a combination of like all three laws. The forces have to be equal and opposite by Newton's third law. So what I'm banking on is the fact that the sledgehammer has a relatively small amount of mass. So I want it to have a big acceleration, and that's going to make it slow down. I'm going to have a large mass, so I'm banking on me having a small acceleration. Because I'm going to have a lot of inertia, so my body wants to remain at rest. The sledgehammer has inertia, but not as much, because it doesn't have as much mass. So this is a situation where we're going to look at all three laws together. And remember, the only thing that affects inertia is mass. Okay, that's it. Nothing else. The only thing that affects it is mass. Okay, got the idea. All right, so, you ready, Ricky? Okay. All right, so we're going to have to take,
Imagine I missed.
you're going to have to take that camera, and we're going to have to take,
I got the computer.
who's got the computer? You got the computer?
Yeah.
Okay, you got the computer.
So I gotta take this thing with me?
Yep.
All right, bro. GoPro time.
And then,
Hey, no, got the computer.
can one of you do that filming?
Yeah, I got the computer.
Okay. If you want to get your cameras on your phone in case something happens when I get killed and it's filmed.
Oh, Calvin, can you grab my phone for me? It's in spot 21.
Okay.
Put it down.
For a cinder block back there?
Yeah. Every year I go by Sublime.
At least you have the
Hey, can y'all?
Yeah, no, yeah, hit it with the flat end, okay? Let's hit it with the flat end.
Hold on. I know it's sideways.
I think this is the first time in my life I ever swung a sledgehammer at someone.
Wait, hold on, Mr. Burkamp, it's still sideways.
Okay,
Does anyone else want to hold this?
okay. All right. So yeah, lay it down this way.
Can y'all see fine? Give me a nod.
Okay. So, you're going to hit with a negative downward force. The block, hopefully, exerts a positive upward force.
Hopefully.
You accelerate a lot, and hopefully I don't. Okay? Now, you're not trying to like win the carnival prize, okay, at the state fair for
I'm
the
glad you
hardest
said
hit,
that.
okay? But you can do a good, solid half swing. Because it actually hurts worse if you don't hit it hard enough and it doesn't shatter, then all that energy gets transferred into my chest. So I want you to hit it hard enough to where it shatters, okay? But not so much where you drive, not so much when you drive it into my chest, okay? No pressure, Ricky, okay? All right, no pressure, all right.
Making me kind of nervous out here.
No one's ever missed, okay?
Be the
Makes
first.
it even worse now.
I'm just saying, all right?
My phone out.
All right.
One
you
second,
ready?
1 second. No, we're not ready. The camera is having technical difficulties. All right, we're now ready.
Okay. You ready? Oh, boy! That was a good hit. Wow. Oh. All right. Oh. That was good.
Did y'all see that?
That was a lot harder
Was
than the
that
first
good?
one.
I feel like I'm a lot bigger than a lot of people.
Huh?
I feel like I'm a lot bigger than some people.
Oh.
That was getting real
Lots
long.
of John.
I should have gone like full over edge.
Not enough Happy Gilmore style.
Way over it.
Yeah, okay.
Oh, shoot.
All right. Oh. All right, here, help me. Okay. Oh. Yeah, that kind of shattered.
Post-game interview.
Yeah. How does it look?
You like, put it in slow-mo, Aiden.
Yeah.
You gotta flinch a little bit.
Oh, wouldn't you? Hello? My God, I'm laying there, a 54-year-old man laying there with a teenager hitting with a hammer. And that's generally a recipe for disaster. Okay. All right.
Ready?
Yeah, it's like bam. Okay, so while we're back here, so bring the cameras, we gotta move over
Hey,
here.
can someone, hey, Aiden, we're moving again.
You got it, bro. You're literally holding it like your hand.
Why did I sign up for this, dude?
You volunteer?
Why do you grab it and hand it to me? You already hold it.
Okay.
Aiden, send that to me.
I got you, Aiden.
Send it to me like in the chat so I can like save it.
Okay, so what we have
Change
here,
it later, taller. Yeah.
so we're gonna make like a miniature
You got
rocket
it.
sled,
You're fine.
okay? So. Take this on.
John, you're so lazy.
Doing too much.
Just hook it to the, just hook it to the computer.
Pants right here and then it can face out.
Your arms are gonna be
Okay.
sore. Yeah.
Okay, so I've got this balloon,
I can hold it. Okay.
and I'm holding this in. So when I let go of it, what's it gonna do? It's gonna accelerate, right? So what has to be happening to cause an acceleration?
The change in velocity.
Change in velocity caused by a force, right? So there has to be some imbalanced force. So why isn't it accelerating now?
Because
There's
there's
a change
equal
in
force.
velocity.
I meant,
What'd you say?
I said there's equal. For you, John?
Yeah, or all the forces are balanced out,
Yes,
right?
that's what I meant. Force.
So I've got gravity pulling it down, I've got the string holding it up, but here's what's important. What's giving the balloon shape? What's the air doing? By the way, I hate the word air molecules. Do not say the word air molecules. There's absolutely no such thing as air molecules. But what's the air doing?
Chill out, I don't know.
Now, if it was chilling out, the
Oh, it's-
balloon would have no shape.
It's forcing the balloon out.
Hold on, John. What's this?
It's I forgot. Miss Shirts taught me this. What's it called? I know what it's called, but I can't explain. I just know
There's
they
a lot of
move really
interactions.
fast.
Define interactions.
The molecules bouncing off each other.
And they're bouncing off
It's creating pressure.
by
The
bouncing
molecules taking up a lot of space from bouncing off each other.
By colliding into each other.
and to the
Balloon.
balloon, right? Because if they don't collide with the balloon,
John's about to
then you're not
record
going to have any pressure. So what's happening is that these particles, nitrogen and oxygen, mostly nitrogen, it's bouncing off the sides of the balloon. And that's what's creating force, because they hit and they bounce back. So this is like if you imagine like a, God forbid I ever teach this, a room full of like second graders, all named Timmy, okay? They're annoying little brats. And they're very hyperactive. And so we've got these room full of Timmys, and they're like, ah! And they're spazzed out, and they're hitting the sides of the classroom, and they're bouncing off, and they're coming back. And that's what's creating this pressure, okay? So right now that nothing's accelerating, right? But as soon as I let go, then hopefully it shoots off down to that end. So here we go. So we'll see what happens.
The nitro kicks in.
Okay? All right? So it accelerates. All right. So now, we do this again. Different form. Kind of one hit wonders.
Good job.
Okay? There's somebody Ricky, turn me off like a couple pieces of tape. About
This
4
is
inches
Ricky
long.
taping.
I'm doing so much today.
I know.
There's a muscle boy.
There's what?
I was talking about
Oh.
there's a shoe game.
What is this? You're gonna push me over.
Such a troll. Such a troll. Let's get down the chat this way.
Okay, so now we're going to do this one.
So y'all let me know in the chat if you can put it all right.
But now, I'm going to put up a shield. Okay? So now we're going to have a glass shield.
There's not a shield. Shield void.
Okay?
We're in it.
Okay, so now I'm going to let go of it. Okay? All right? So we're going to go 3, 2, 1. Okay? That was it. So the only difference was in between the two is that this was a blast shield, and the other one was just shooting off into empty space. So here's what I want you to do, is that I want you to go back. You're not going to hand this in. This isn't any kind of grade. What I want you to do is draw the two different mechanisms about if the blast shield affected the system in terms of how, what was physically happening to make that balloon go down the road. So in other words, where were the forces happening? Did the blast shield play a factor at all? If so, what did the blast shield do? So I want you to go back. I'm going to give you like a couple minutes. All I want you to do is just make a simple sketch between the two systems. One with the blast shield and one without the blast shield. Okay? Okay. I'll take that.
Thank you.
Watch out, Rich.
That's the man behind the camera.
John, I have a feeling they do not like it.
Oh, no, they don't.
Where was this?
David, focus on David. What? There's not. That. Okay, Ricky, you're the computer dude. You got it straight.
Look at that.
You can make this thing like super upright. Oh no, you can't. That thing's not bendy at all. Why would that not bend?
So you want two separate ones, one with the blast
Is that
shield?
good?
One with the blast
No, it needs
shield.
to be up more.
Okay?
Stay.
So somebody should be able to look at your paper and figure out how you think that force is acting to propel that balloon down the stream. Like where the forces are, where the forces are acting and what they're acting on. time I did that at a grade school, nails, and I had a jacket on, but underneath that I had a white shirt, and I'd taken a marker and I put little red dots across the back. And so when I get done, I took the jacket off, and the kids, I had my back to the kids, and they saw like the red dots, and they thought I was bleeding, they're all flipping out. I'm like, no, it's just some red dots, that's okay.
I thought you were gonna have like a little blood, like things for like when they smash.
Yeah,
Little
it-
capsules.
Well, it was bad enough with the red dots, so the kids were fairly traumatized, so I wasn't invited back. I thought it was funny, but apparently trauma and little kids, this is a bad combination.
Mr. Burkamp probably has a record for the amount of times hit by a sledgehammer.
Huh?
You probably have a record for like amount of times hit by a sledgehammer.
It wouldn't take much, you know. Since that was built about
Did you build it?
20 years ago. No, I had a TA built it. It was horribly built because you had to pre-drill all the holes. Because if you not, then when you drove the nails through it, it would just splinter the plywood. And there was like 100 pounds of nails. So yeah, I had a kid drill,
Okay.
and then pound. Yeah. Yep. Okay, Jeff Weisenbach. Okay. So let's talk about the one without the glass shield. Okay? So what's your mechanism? So this is this top one without the blast shield. So what was happening to make it go down the road?
The air flying out the back.
The air flying out the back. Okay? All right, that's one force. So how is this air flying out the back making that go forward?
It's propelling it.
But
There's an offset force.
what'd you say?
There's an offset force.
What's the offset force?
The air. I don't know.
The balloon pushing out. The air and the balloon pushing out.
Kinda. Okay, let's visualize this, right? So you've got Nancy, the nitrogen molecule, and Ollie, the oxygen molecule.
Do you mind if we borrow John for an interview? For broadcasting?
Well, he just went to the restroom, so if you wait for him outside,
Alright,
take him.
appreciate it, thank you.
Not a problem.
We don't want that.
It's like, John, you changed, man. Okay, so, weird. Clothing and everything. Okay. So, you got Nancy, the nitrogen molecule, and Ollie, the oxygen molecule. So what's happening inside is that these particles are bouncing off, right? And every time they hit, they bounce back. So it's just like me taking this golf ball, right, and throwing it against the screen. Every time it hits, it exerts a force on that screen because it has to bounce back. Okay? So this is happening billions upon billions upon billions of times, right? So you have this basically a repulsion of electron clouds. And they're hitting, they're bouncing up. So when it's closed up, right, you have an equal number of collisions all the way around. And that's why it maintained a symmetrical shape. So when I let go of it, okay, all of those particles which were trying to hit the back of the balloon, right, now have an escape route. Now they're going to go out the front. But here's the question. Why, when I let go, why didn't the balloon accelerate upward or downward? Why didn't it go this way?
Chose the path of least resistance.
Kinda? Jennifer?
It has air molecules hitting both up
Did you
and
say air
down.
molecule?
I'm sorry.
How about nitrogen and oxygen molecule?
Yeah, those.
And they're hitting equally on both sides, right? Okay? They're hitting equally on both sides. But look what happens in the front. You still have these particles hitting the front of the balloon, right? But you don't have them hitting the back of the balloon. So what's creating this force to make it go forward is the fact that you have particles that are hitting the front, okay? But you don't have a balanced force in the opposite. So the action-reaction force is happening in the front of the balloon. Okay? That's where the action-reaction is taking place. Because on the back, Nancy and Ollie are out of there. They're gone. Okay? They have left the balloon. Now, here's the question. Does the blast shield have any impact at all on the forward motion of the balloon? Some say yes, some say no. Calvin, you say emphatically yes.
Yeah.
How?
I think-
What's the mechanism?
I think it's providing an opposite force, so it pushes it back. So like jump starts the process.
Okay, so let's look at a single oxygen molecule, okay? Right? So we're going to draw this a little bit bigger, okay? So here's the back of the balloon, right? And here's the shield. So all of the oxygen molecule leaves the balloon, right? So this is a single particle. This is like this golf ball, right? There's the balloon, and it's going to hit this shield. So it's gone out here and it's hit the shield. What's it going to do when it hits the shield?
Bounce off.
Okay? Then it's going to turn around and go this way, right? So will that interaction right there, when that oxygen molecule hits this and bounces off, will that have any impact at all on the balloon itself? When all of the oxygen molecule hits the blast shield, okay, is that reaction there going to have any impact on the balloon itself? No, because it's happening out here, right? Okay? That's happening here. It isn't happening inside the balloon, it's happening here. Now, you could make the argument that, well, maybe after that oxygen molecule hits here, it's going to bounce off and then hit the balloon and push the balloon that way. Okay? Well, but here's the deal. As soon as I let go of the balloon, which direction did the balloon go? It went this way. So the balloon has left the scene. So yeah, that oxygen molecule is going to hit, and I'll grant you, it's going to bounce back. It's going to create a little bit of an action-reaction force here. But that is a completely separate system than what's happening with the balloon. So the blast shield has nothing to do with the story whatsoever, because that interaction there isn't what's making the balloon go forward. The action-reaction that's taking place is up here in the front of the balloon. That's where the action is. Okay? So, because if you had to have a blast shield for rocket engines to work, and this is what it is, it's a very crude rocket engine, then rockets couldn't operate in space. Because if you had to have a shield for the rockets to push against, if you were in a vacuum of space, it couldn't work. But because the action-reaction takes place within the rocket engine itself, that's what allows us to use rocket engines in space. Okay? So the shield had nothing to do with it, because it physically can't transmit that force back to the balloon. So they're both happening up here. Okay. So here's the next thing that we want to look at. I want to get an idea of how much force is generated by the fan on the fan card. Okay? So obviously when I set it down, I get an acceleration, right? Okay? So if you look at this in terms of forces, so here's the fan cart, right? And I set it down, and the fan cart's going to take off and it's going to move. So what has to be acting on the fan cart? Somebody said it. What has to be acting on it? Well, gravity's going to be acting on it, right? So gravity's going to be pulling it down. What else is there?
A force.
What?
A force.
Acting which direction?
That way.
That way, right? Okay. So I got a force. So I've got gravity pulling it down. I've got some force applied, which is making it move, and there's going to be a third one. What's the third one? There's a little bit, not much. We're sitting on a table, right? So what else has to be there? The normal force, right? So the table is providing an upward force. So I've got a force applied, a normal force, and a gravitational force. These aren't going to add up to equal to 0. That's what's going to make this thing accelerate, right? Now, so what I want to do is I want to find the mass of this cart, because I'm going to use F equals ma. So what I can do is, just give me that right here. So how can I find the weight of the cart? Let's start with that.
You hang it from the hook.
Yeah. So I hang it from the hook, and the hook says that it weighs 4.25 newtons. So if the fan cart weighs 4.25 newtons, then what's the value of my normal force? Don't make this difficult. 4.25, right? Okay? 4.25 newtons. These forces are balanced out. Now, here's the question. How can I find if I know the weight of the cart, which I do know, how can I use that to find the mass of the cart in kilograms? What's the simplest? What do you multiply together to get the weight of an object? Mass times your gravitational acceleration. So if I know this number, and this equals mg, how can I find the mass? No. We know the acceleration caused by gravity. What's the acceleration caused by gravity?
Negative 9.8.
Negative 9.8 meters per second squared. So if this here, right? So negative 4.25 newtons equals mass times negative 9.8 meters per second squared. So this is what you all are used to doing. You all are used to taking the mass and multiplying it by negative 9.8 meters per second squared to get the weight. So if you know the weight and you're trying to find the mass, what can you do? Divide by. So somebody take a calculator and take negative, or just take 4.25 and divide that by 9.8. Hey, what'd you get?
0.4336.
So 0.434
Yeah.
kilograms. Okay? Right? That's the mass. I have F equals ma. I have half of it. I have the mass part of it. But I don't have the acceleration part. So what are some things that I can, when I turn this thing on, okay, and get it up to speed, what are some things that I could potentially measure? Huh? I can measure how far it goes, right? So I could, and we're going to do this. That's why there's a meter stick there by Angelique. I'm going to let it travel 1 meter. I'm going to measure a distance. What else could I measure?
Time.
Time. Now, if I'm clever, what am I going to let the initial velocity of the cart be? 0. So you all know that distance equals 1/2 at squared plus v naught time. So if I know the initial velocity is 0, I'm going to start this thing from rest, so I don't have to worry about this. I can measure distance, like Tyler said. Okay, I can measure how far this thing is going to go. I'm going to have Ricky sit there with the stopwatch. You're on a roll, man. Okay? I'm going to have Ricky measure the time. So the only thing I'm not going to know is the acceleration. So Paige, I need this solved for acceleration. So what am I going to do?
Subtract v naught time and then divide.
Yeah, I don't even have to worry about this because this is 0. So don't even worry about this.
Divide distance by time and 1 half.
But I hate fractions, so what am I going to do? Instead of dividing by half, what am I going to do?
Make it a decimal.
No, that's even worse. Let me give you a hint. It rhymes with multiply by 2.
Multiply by 2.
Brilliant. Okay. So I'm going to multiply by 2 because I hate fractions. So I'm going to have 2d over t squared is going to equal my acceleration. Okay, so gentlemen, let's have suspended the cameras over here. So, Ricky, you get ready to time. And we're going to let this thing travel. Are the cameras
You got it,
fine?
Chazzy.
So, just take the books, just spin the books.
Oh, that camera.
Okay,
Is it good?
okay, got it?
Stopwatch.
Ricky, you ready to time?
Oh yeah, I gotta get exact measurements on it.
Okay, all right, I want you to get exact, man.
Yeah, absolutely, down to like the 100th second.
Okay, so I'm gonna have the fan up and running. Okay, so I'm gonna go 3, 2, 1, go. All right, you ready? 3, 2, 1, go.
2.74.
2.74, okay.
You know, sounds right to me.
Yeah, not quite a speeding bullet, but not bad. Okay, so. So, we're going to take 2 times 1 meter. And what was the time?
2.74.
2.74 seconds squared. Okay, so somebody take 2 and divide it by 2.74 squared. Oh, come on.
You can get a calculator.
0.730
0.730
meters per second squared. Yeah.
meters per second squared.
Oh, wait, no.
What?
Forgot to square it. Hold on.
Okay.
0.266.
0.266
Yeah, that's the right one.
meters per second squared, right?
Sure.
Okay. So, now I know my acceleration, because and here, acceleration is really tough to measure, especially if you're trying to measure like that ending velocity, because, okay, I got the initial velocity, because the velocity is always changing, that's tough to measure the actual velocity. So this is the easiest way to calculate acceleration, and we're going to use this process a lot, okay? So we can always measure distance, we always let the initial velocity be 0, and then we can measure time. So get used to this. We're going to use this process a lot to find accelerations. Now all we have to do is F equals ma. So we said the mass was 0.434 kilograms, and the acceleration was 0.266 meters per second squared. So Aiden, take 0.434 times 0.266.
0.115.
0.116
116. Yeah.
newtons. So that's the force that's available to accelerate the fan. Okay? Now, here's what I want you to look at. This is the force created by the fan, 0.116 newtons. It weighs 4.25 newtons. Okay, so the force from the fan is 0.116. It weighs 4.25 newtons. So if I took this fan and turned it vertically like this, would the fan produce enough force to make the make it act like a helicopter, and would it begin to accelerate upward? Aiden, you shake your head no. Why?
Because the force normal is greater than the force it's able to produce.
Not so much the force normal, the gravitational force.
Okay.
Okay? So I've got a downward force of 4.25 newtons. When this thing is on, I only have an upward force of 0.11. So even with this thing at full speed, if I let go of it, it's still going to accelerate downward, because the force from the blades isn't enough to overcome the weight of the cart itself, and so it's just going to fall. Okay? Now, it's not going to fall as quickly as if the fan was off, because it is going to provide a little bit of upward force, just not enough to make it hover. Okay? Got that idea? Okay. All right. So, let me hand out a bunch of papers, so stop that camera for a second, while I hand out papers.
What button is
There's
it?
some high tech
The red
stuff
one?
up there. Or then maybe the on and off button.
And I couldn't access it, and then,
I'm gonna be
Oh
on
my God.
YouTube now.
okay.
Pretty much just select
So,
it.
let me kind of go over a couple of things on this purple sheet assignment 401. Now, listen to me. I do not want this sheet handed in to me, okay? You are going to treat this like a textbook page. You can write on it, you can do whatever. But do not answer a single thing on here that I am going to grade. Not the multiple choice, not the problems, nothing, okay? I do not want to see this again. Do not scan it and send it to me. I know what the questions are. I wrote them, okay? I don't need to see these again. So even on the multiple choice, you are going to answer these on a completely different sheet of paper. You're going to draw a line. You're going to have the answers over here, and you're going to have the work over here. Okay, so there's a couple of them I want to make sure everybody's cool with. So on question number 6, okay, I'm going to read this because it sounds a little daunting. So if with no friction a force F results in an acceleration A when acting on a mass M, then tripling the mass and increasing the force 6-fold will result with an acceleration of, and you're going, what is this even talking about? So I'm going to show you a couple of different ways that you can do this problem, okay? The basic idea is you start with F equals ma. So this is question number 6, is F equals ma. So one option is that you do what's called smash mouth physics, and you just make up numbers, okay? And some people like this process. So what's the easiest possible set of numbers that I could choose to work with?
1/2.
No, easier than that.
1.
1, I can't do 0, okay? Because 0 math just doesn't work, okay? But I could say, oh, a 1 Newton force acting on a 1 kilogram mass would result in an acceleration of 1 meter per second squared. Okay, that's the definition of a Newton. Is how much force is needed to take a 1 kilogram mass and accelerate it at 1 meter per second squared. Which, now, if you all kind of visualize the acceleration of the fan cart, right? So when that's turned on, that's like an acceleration of about 0.26, okay? So an acceleration of 1 meter per second squared would be about 4 times faster than that. Okay, so you can kind of get a visual of what that would be. Now we're going to change the system. Okay, so now we're going to triple the mass. So instead of 1 kilogram, it's going to be 3 kilograms, right? The force is going to go up by a factor of 6-fold. So instead of 1 N, it's going to be 6 N, 6 newtons, right? So to make this thing balance out, what's going to happen to my acceleration? It has to be 2. So my acceleration is going to double. So if I increase the force by 6, I triple the mass, that means my acceleration is going to go up by a factor of 2. Now, that's if you like smash mouth physics. I'm going to make up numbers. I'm a numbers kind of person. I'm happy for you. Okay? Now, there's a little bit more of an elegant approach that you can take. You just start with F equals ma. Okay, that's the basic equation. Now I'm going to triple the mass. So I'm going to write that as 3m, because that's what it means. It's going to be 3 times the mass, right? So what am I going to do with the force? 6F, right? So then to make it balance, my acceleration has to be 2a. Okay? That's the other way that you can do it. If you like variables, go with this. If you like smash mouth physics, go with that. Okay? I don't care. It's up to you. It's whatever works. When you get to number 4, when it talks about a jet plane taking off, I want you to reference both of Newton's laws, the first and the third. If you don't know what those are on your lecture notes. First law basically says you want to stay at rest. Third law says, hey, there's an equal and opposite reaction. So the chair is pushing you forward, you feel the equal and opposite force going backwards. That's the short version. Now, when you get to number, like let's say for example, number 4. Okay, so let's talk about this is problem number 4. So in problem number 4, here's what you've got. I've got a 500 gram mass, looks like yay, and I'm going to put it on a scale that measures in newtons. So here's my question. What should be the reading on the scale in newtons if you have a 500 gram mass? So how can I figure out what a 500 gram mass weighs?
Acceleration,
Acceleration caused by?
gravity,
Acceleration caused by gravity is?
negative 9.8.
And the mass is going to be 500 grams, but we need to change that into?
5 kilograms.
So is it 5 kilograms
Oh,
or
no.
0.5 kilograms?
0.5.
Let's go with 0.5, divide by 1,000, multiply that by G, I get 4.90 newtons. Okay? So the reading on the scale should be 4.90 newtons. Now, so visualize this. You got gravity pulling it down, right? So the scale is measuring the upward force that it has to provide to balance out the downward pull of gravity. So what we're going to do next is I'm going to take a balloon and we're going to attach the balloon to the weight. And then you're told on that one that the scale now reads 4.80 newtons. Okay? Now it's reading 4.8. So, but it's not accelerating. So what do all the forces still have to add up to? 0. So I've still got gravity pulling it down. That hasn't changed. I've got the balloon providing an upward force, right? And the scale basically is making up the difference. Okay? So when you get to 4D, draw a free body diagram, you're going to have on 4D, you're going to have 3 different forces. You're going to have the force from the balloon, you're going to have gravity acting down, and then you're going to have the force normal from the scale. So on number 4D, you're going to have 3 different vectors. You want to, not only do you want to draw them, you also want to state what those numeric values are. Okay? Now, when you get to number 5, on the back side, yes, there's the back side. So when you get to question number 5, here's the setup. You got a block of wood, 4.80 kilograms, and you're pushing this block of wood at 5 meters per second like this. You're pushing it at a constant velocity. So what do all the forces add up to? 0. So what are the 4 forces acting on this block when I'm pushing it at a constant velocity? Chasley, what's one of them?
Force applied.
Okay, so I've got my force applied going this way. What else?
Force normal.
Force normal?
Force friction.
Force friction, which direction is my frictional force going to act? Opposite of my force applied. And I got one more. Gravity. Now I have my mass. Okay, I got a 4.8 kilogram box. So I can multiply 4.8 by G and get my downward force. That's going to also give me my normal force because of the fact that it's sitting on a flat surface. So here's the deal. I've also given you mu, right? So mu is 0.380. So how can I, knowing mu, how can I find the value of my frictional force?
Multiply it by the force normal.
Right. Because mu equals force friction over force normal. So on 5A, you want to find the horizontal force that has to be applied. So on 5A, you want to take mu times force normal to get your force friction, which is the same as your force applied. Now, if 5A is wrong, everything is going to be wrong. Your answer to 5A should be something close to your current age. Because literally, if 5A is wrong, everything is going to be wrong. Okay? Something close to your current age. So here's what's going to happen. We're pushing this thing along for 6 seconds, and then we're just gonna stop. Like, screw it, I'm tired, I'm not gonna push anymore. As soon as I stop pushing it, what does the block begin to do? Accelerate. Why? What do I lose once I stop pushing it?
Force of flight.
Force of flight. What's still there?
Friction.
Force friction is. Okay? Now I have an imbalanced force. Guess what? Now it's going to begin to accelerate. Okay? So, that becomes your imbalanced force. Then you're going to use F equals ma. So that's your force. You still know the mass of the block. Use that to find the acceleration. Now, when you're doing these on your sheet of paper, do me a favor. So like at number 5, you have all these different parts, okay? So have like the answer to 5A here, and then whatever work that you have over here. And then the answer to 5B, and then here's going to be 5C, and have that work. Keep this work beside these different parts, okay? Don't stack your answers up here and then have your work running down to the bottom of the page, or worse yet, on another page. I will flip out, okay? And you're going to work these in sequence. Don't jump around, okay? So, leave me space. I beg of you, keep this organized, please, okay? All right. Now, when you get to E, on 5E, you're going to draw a velocity time graph. So let me get you started on this. And you can do this on your paper. You don't have to do this on an actual sheet of graph paper. This is just going to be a sketch. But draw it big enough where I can see what's going on. So you got a velocity time graph. You're moving at 5 meters per second for 6 seconds. So how far did it go at 5 meters per second for 6 seconds?
30 meters.
What'd you say?
30 meters.
30 meters, okay? 5 meters per second times 6 seconds, this thing is going to travel 30 meters. Okay, cool. Now, I'm going to stop it. At this point, what's the velocity time graph going to do? Aiden, you have 3 options. I'm going to stop pushing the block. It's either going to go up, indicating that the block is going to speed up. It's going to just maintain a horizontal line, or it's going to slope down towards 0.
It's going to slope down.
Now, the slope of this line is going to be the acceleration, which you just found up above. Okay? You found the acceleration. So what you want to do, this is going to be 30 meters. You want to add to it that distance. But here's what you cannot do. Don't use the 6 seconds that was already pushed. Okay? That isn't how long it's going to take to slow down. Here's what you're going to know. This will make sense when you get to this problem. You're going to know the initial velocity is 5 meters per second. You're going to know the final velocity is 0. You're going to know the acceleration. Find the distance. So to find the distance, you're going to take 30 and then add that to what you get when you use that equation, v squared equals v naught squared plus 2ad. Okay? So that's what you're going to use to find that distance. Okay. All right. When you get to number 9, let me kind of give you a visual on number 9. So this is actually what happens. This guy jumps out of a plane. His parachute doesn't open. He's in Alaska. He lands in a very, very deep snowbank. So here's the snowbank. The guy craters in, and the depth of the impact is 1.07 meters, which is about like EA. Okay, so it isn't like he hit concrete. So he landed in some snow and created an impact crater this deep. I tell you this, that he hits going 53.6 meters per second. So that's how fast he was going at the point of impact. What's his final velocity going to be? 0. So V naught is going to equal 53.6. The final velocity is going to be 0. You want to find the acceleration, and you know distance. Use that equation. So in number 9, you're just going to use F equals ma. You got to find the acceleration, multiply that by the mass. There you go. Okay, so I would suggest by tomorrow you might look through these. If there's any ones that you want me to explain when I'm giving this lecture, on net forces, then email me, say, hey, Burkamp, hit on number 5 or something like that, okay? All right, we're done. Good luck. See you all on
Friday.
Are you guys doing English?